we've been talking about the birthday problem, which we can phrase as this probability, the probability that among n people, at least 2 of those people have a birthday in common is given by 1 minus the product, or the probability that they don't, which we computed last time is the product from k equal 1 to n minus 1 of 1 minus k over 365. Because this is saying that I don't match any of the k people who came before me. We're going to see how to use that to do an attack on a hash function. So what's a hash function? Just at sort of a high level. You take an input message and you return a hash, which is a way of encoding it. Now your input message can be arbitrarily long, but your output is going to be a fixed length. So let's assume that there are n total outputs for your hash function, h. And we're going to see that actually you need to be really careful on how many things you hash in order to make sure you don't run into a problem. Here's the statement of the theorem. For n large, which it generally is in applications, hashing the square root of n values will likely lead to a collision. So we're going to make this statement mathematically precise, but this is the sort of statement that we often get when we're doing an analytical analysis of a statement like this. So we often want to make statements about n being large, so we can do some kind of asymptotic estimations, and then we're going to get bounds that are going to be on the order of magnitude of something. There's going to be a constant, and we'll see what it is in this case. And this isn't going to be a precise result, but it's going to be an approximation, okay? Here's how the proof goes. So we're going to use the birthday problem to start us off. So we're going to have the probability, let's let P of n, for this context, be the probability that we have a collision. So probability that 2 outputs happen the same for n inputs. So because we have a fixed number of outputs that we can put for our function, if we put in n inputs, what's the probability that we're going to have a collision? This is like saying if we have n people and the possible outputs are the number of days of the year, the day they were born, what's the probability that we get a collision? And we can see from this formula, this is just going to be 1 minus the product from k equal 1 to n minus 1, 1 minus k, not over 365 anymore, but over n. What's the size of our output space for our function, our hash function? Now, we want to do some analysis on this, and because we saw we could write this as a following factorial, but that's not a function that we can do nice analysis on. So we're going to need some kind of a lemma. So here's the lemma that is actually going to come in handy, and this is a typical sort of estimation that you're going to get when you're doing this sort of analytic combinatorics. So if I have a sequence, say a sub n, and the terms go to 0, okay, and when I scale them, say n times an, they go to some fixed value x. What this is saying is that our terms grow linearly. They grow kind of like n. Okay, then I can do some estimation that 1 minus a sub n to the power n goes to e to the minus x. So let me just say, I'm not going to go into exact details of this proof, but it really follows from this precise statement that you've probably seen in calculus, which is that we can write e to the x as the limit of 1 plus x over n raised to the power n. Okay, so this is one way we can think of e to the x, and we can use that to prove this statement. Let's use this statement. Now here, what are we thinking of? We're thinking of estimating each of these terms inside here as our sequence, 1 minus a sub n. Right? So each of these terms, as k is growing, right? So we're thinking about n's getting big, so this k is getting big. So these are going to satisfy these hypotheses, and so we're going to be able to approximate this. So using the lemma, we're going to say this is approximately equal to 1 minus the product from k equals 1 to n minus 1, and now we're going to use our estimation, e to the minus k over n. So this is by the lemma. And this is really the first step that we're often going to do in these combinatorial things is we're going to make these estimates. And this happens because this is a precise statement about limits. When we say that we're doing an estimate, we're saying, well, as n is large, once we get close to infinity, this happens. Okay? And of course, we can make this very precise if we want to, and we can get our error terms and all of that, but let's just keep it at this high level for now. Let's think about what happens when we expand this out. So this is going to be 1 minus, well, one of the very convenient things about doing this product is now I can say what happens to the exponents. This is going to be e, the exponent becomes the sum from k equals 1 to n of minus k over n. This is just using the fact that exponents become additive. But okay, I can still work with this. I can see that that is going to pull out my denominator there. So I have 1 over n, the sum from k equals 1 to lowercase n of minus k. Actually, I'm going to pull out that minus sign too. And now I'm just adding the numbers from 1 to n. So I know how to do that. That's something that we did in one of the very early sections of this class. So I get 1 minus e to the minus n times n minus 1 divided by 2, and then don't forget our n. Okay? So this is here, and then this is what I get by taking this summation. Okay, so what is that? Well, again, I'm only doing things approximately anyway, so I might as well make another approximation. There's not much difference between n and n minus 1 when n's huge. So let's use that fact and just make this a little bit cleaner. So this is kind of like e to the minus n squared over 2n. They're roughly the same, right? As n's big, there's not much difference between n minus 1 and n. Okay, so now we have an estimate for our probability. So let's put that all in one line maybe. So we have the probability of a collision with n inputs when n is big is roughly equal to 1 minus e to the minus n squared over 2 to the output size. Okay, so what do we need to do now? The next step that we're going to have to do is solve for n, and then we're going to set the probability equal to 1/2. That's what we mean by likely. So when it's likely to happen, let's say it's got a 50% chance of happening. And of course, depending on what your specifications are for how secure you want your hash function to be, you could change this parameter that you set it to. We're doing something that's completely general. Okay, so let's see how that derivation is going to go. We've got this. We need to solve for n. So I'm going to say, okay, well, p of n minus 1, and actually, let's just go ahead and flip that around to 1 minus p. 1 minus p of n is roughly equal to e to the minus n squared over 2n. So that's the first step. Now I'm going to get my logs coming into here. So we're going to have to take the log on both sides. That's going to reduce our thing. We're going to get, I think I'm going to flip the sides of the inequality just so that it looks a little nicer. So we're going to get minus n squared over 2n is equal to log of 1 minus p of n. And now, when I put the minus sign over on the other side, remember that exponent can jump inside the logarithm. So I'm going to use that to keep things looking nice and clean. So this is going to say that we can get n squared is equal to 2 capital N. I've multiplied that across, and now my minus sign I'm going to deal with like this. Because this is a nice value, right? 1 minus a probability, well, that's going to be a number that's less than 1. So this is sort of a nice way to represent it. And now I need to take the square root, right? So what are we going to end up getting? So I end up getting, in the end, that n is approximately equal to the square root of 2 capital N log of 1 over 1 minus p of n. And now I can set p equal to 1/2. And what do I end up getting? I end up getting that n is approximately equal to 1.177 square root of capital N. So what does that mean? That means when I take this many inputs, I have a 50% chance of having a collision on my hash function. So when I take about the square root of capital N, when I take that many inputs, it's likely, more than half a chance, that I'm going to end up with a collision. So just to make this a little more realistic, if I take a 64-bit hash function, that's going to have a collision in about 5 billion attempts, which actually is not that many.